Alrighty. So your lab 0, sorry, that's lab 0. Your lab number 1 is due tomorrow at noon. And please make sure to submit in time. No late submission will be accepted. It's going to be closed automatically. Do just submit your best attempt before the deadline. I think there will be some uses expected about sets relations in lab number 1, but based on the tutorial, you might be able to find the resources yourself. But after the math review lecture, I think everything will definitely make sense. I'll release a solution very soon after the deadline, either later tomorrow or maybe early Monday. So you can take a look. On next Tuesday, we can go over some parts of lab 1. Just make sure you're okay. And I will also release lab number 2 tomorrow, so you can also start working on that. That one definitely has to use something about sets and relations. But we are just doing that starting from today. So should be just good timing. All right, and I want to just draw your attention to one of the announcements I made yesterday, just in case you missed it. If you go to the eClass site and go under announcement, I think I had announcement yesterday, a very useful document for Event B Math Toolkit. If you click on that, a very useful PDF document. So that one basically summarizes all the predicates, propositions, and sets relation operators that you can use for your rodent projects or even on paper. So I'll just give you one example. Let's say we have, let's say universal quantification, right? This one here. Basically, this is the name of the operator. And this one here is the form on paper. And this will be what you have to type on rodent. Very useful ASCII syntax. And also, this will be some informal or formal description about what the operator means. So it summarizes basically everything you would need, okay, for rodent. And I would suggest keep this document handy there, and you'll find them very useful for subsequent labs as well. And for any operators that we might discuss today, for example, power set, set union, set intersection, things like that, you can always find the reference over here. Again, very useful documents. Please take a look. And not that many pages. If you want to print them out, you can feel free or load it on your iPad. Up to you. Okay. Let's have a very quick recap about where we are. And then we'll move on to the next phase of the review. So last time we talked about still mainly predicate logic. And we started with this connection between empty range over here in math versus empty array in programming about the different base cases, right? Make sure you understand the connection. And we talk about the difference between conjunction versus ampersand in programming. They are not exactly the same. Another thing which I forgot to mention, right, which I can put right now. If you think about it, so when we talk about math, oh, sorry. Let me reconnect my Apple Pencil. Sometimes it's kind of write very funny. Do it again. If you think about math, we have something called commutative rule. If you kind of remember what that really means, right? But I'll show it to you. When we say P and Q, it would be equivalent to Q and P. That tells you the order of the operands over here for conjunction doesn't really matter. However, if you talk about Java, when you say P and Q versus Q and P, they are not the same, right? Because we talk about short circuit evaluation. For Java, you have to go from left to right evaluation. If this one already evaluated to false, you never get a chance to get to Q, which may be undefined or crashing, right? So that's something I forgot to mention. So you may want to think about that too. It's called commutativity. Commutativity. Yep. Okay, that's just to complete the picture a little bit more. Okay. And then we also talk about the, just some example for short circuit for guarding constraint. And then we'll talk about the different sets, integer, natural number. Just don't forget, for this course, the natural number includes 0. If you really want to use positive natural number, please use 1. But you can put some additional constraint to say it's strictly larger than 0. Up to you, right? You can choose some additional axioms or invariants if you wish. And we talk about you declare multiple variables for quantification separated by comma. Yeah, you might run into that for overlap number 2. And we'll talk about example 4, the 2 quantification and proof strategy. So really understand the different strategies we talk about. In some cases, it might be very trivial for you to prove that one is true or false. But in some cases, you may have to argue the entire range. Right? It really depends. Okay. And just more example there. And that was the final example we did just to do a little bit of proof, just to get used to the proving mode back in 1090. But as I said, when we do proof later, once we start the bridge controller case study, the format of the proof is not exactly this. But the idea will be very, very similar. You have to go step by step by different rule. But that's something we'll get into, right? Do you guys have any questions from last time that you want me to explain? Yes, go ahead. Sorry? I am recording the lecture, yes. Hopefully that wouldn't crash on me again. I really hope. Should be okay. Thanks for asking. More than happy to record. Yeah, so as I said in the lecture, don't worry too much about losing the notes or losing the slides. Just focus on listening to what I'm trying to say and focus on maximum comprehension. That'll be the best for you. Okay, let's now move on to the next phase for the review lecture. All right. So which is about sets. Yeah, question. So the question was, if you submit one of your labs, somehow you couldn't really complete everything, you still submitted that, are you going to get any reduction of marks? No. You'll still get 100%. So the idea would be, as long as you submit the best you can do before the deadline, right, you will get 100% for sure. But I'm hoping that once you will still, beyond the deadline, still try to complete them, either by yourself or maybe by looking at the solution and try to redo it for your learning, because we're going to cover them in the subsequent tests.
Yeah, because it was on your website, it was graded, otherwise that's why I was.
Okay, so don't worry, you're going to get 100% as long as you submit your best attempt before the deadline. That one's guaranteed, okay? No worries. All right, let's now talk about sets, okay? We'll start with something very simple, but I'm also going to give you some practical example about how you can use the sets and do something useful to assert the properties of your program. I do have some example there. Hopefully we can get to power set relation. These are the more tricky bits. Hopefully we can do that, and they can struggle through that a little bit over the weekend. We can continue from Tuesday. Let's see. I'll start with something very simple. A set is just a collection. And we call them elements or members, but usually I'll just say members. Okay. And the order in the set doesn't really matter. And the element can appear at most once in the set. So what does this mean? Let's just see some example. Okay. So let me switch. Sometimes if I forgot to switch on the iPad, please shout to me. All right, let's now see the first one. All right. Let's just see some example here. Number one, about the ordering. Ordering doesn't really matter. So when you specify a set, let's say 1, 2, 3, it just consider as equivalent to 3, 2, 3, 1, equal to. Right? Order doesn't really matter. And you should never write something like this. There should be no repetition. So you shouldn't really write something like this, like 1, 2, 3, and 2, just repeating it. You shouldn't do that, right? Because you got some repetition. Okay, easy stuff. And then we may define a set. So there are two ways for us to define a set. You might find both useful for your specification rodent. The more explicit way is by enumeration, which means you know exactly what members are in the set. It's called set enumeration. Well, for example, I know exactly 1, 2, 3, 4, 5 members in my set. I can just specify them. Let's say, for example, if you want to do a transfer in your bank account, you know that it's going to involve 2 accounts, right? For example, when you see the solution, you will see what I mean, or you already figure out, either way. The second one is actually more interesting. This way here is called set comprehension. You're going to specify the set somehow by constraint, meaning that every object or entity that satisfies the constraint is going to be included in the set. So it's a more implicit way of saying things. So we're going to get more used to this kind of way of specifying. I'm going to give you some example. Let's see if there's anyone on the slides. Okay, let's see here. I'll give you more on the page. The syntax goes like this. Okay, let me switch right away. So set comprehension is going to require a little bit more attention from us. Set comprehension. The syntax goes like this. Curly brackets and curly brackets, okay? And you're going to have a vertical bar in the middle somehow, okay? Now, the left-hand side over here is going to be a list of variables. Oh, you know what? Let me put it this way, since we're going to see example later too. This is going to be some expression, a single expression. Expression representing the form of a member in the resulting set. May not make too much sense to you right now, but I'm going to give you an example. Just bear with me in the resulting set. And what I want you to pay attention to is the word form. Okay, we're going to need that very badly when we define relations. And then, so that's about the left-hand side. The right-hand side is going to be some constraint. Okay, the right-hand side here. Boolean constraint, predicates, or proposition. So this part here is going to be a constraint. Can be as complicated as it might need to be. Okay? Basically, any values, how about this? Values satisfying this constraint will be included as members. Values satisfying this constraint will be included as member. Let's try some example, and you will see what I really mean, especially by form over here. Example number 1. Let's say x such that this is something very easy. All right? Well, that one is easy. I'm saying I'm going to include all such x where x is in between 0 and 2 inclusively. That one's pretty easy. That one would be as if you're saying the set enumeration 0, 1, and 2. Okay? Let's have another one here. What about I want to have 2 variables? Somehow, if you want to have 2 variables, in general, you put some specific form for that. Let me just give you one example that's going to be helpful for understanding relation for later. Let's say I want to have 2 variables, x and y. Each one of them has certain range. I want to include in the final set, x, y being pair. Okay? So what I would say is, each member in the final set is going to have the form, like a pair, x, y. Like that. And then such that I can say x should be a natural number. And y is a member of natural number. All right? Of course, this will be maybe if I just close this set comprehension now, that's okay. It's an infinite set, basically. It's going to include all the combination of such pair where x can be from 0 to plus infinity. And y could be from 0 to plus infinity, right? You got all the combinations, just infinite. Right? That's one example. But let's further constrain so that we can enumerate them as well. How about we just do this, just for our sake of illustration. Let's say and. Let's say 1 less than or equal to x less than or equal to 2. And let's say 3 less than or equal to y less than or equal to 4. All right? Simple enough. Can you tell me something here? So these are the constraints. That's going to make sure we have a finite sets, right? There's another notation, I believe, that's on this slide. I'll come back here. Give me one moment. There is something about empty set, you know that, and also something about cardinality, the size of the set, right? The way we write about cardinality is by using the vertical bar around, okay? So let's not go back to that example. So now for this particular example, if I ask you about what is its cardinality, I'll put a vertical bar here and also a vertical bar over here, right? If I only give you this set, comprehension alone, what you should do is you should enumerate every member in the set, like a set enumeration. But if I simply just put a vertical bar around, I'm asking you to give me an integer telling me the size or cardinality of the set. Why don't we start with the cardinality? What should be the cardinality of the set? 4? Yeah, of course. Okay, in case you haven't figured out, that's okay. You want to get used to it. We also need this kind of a combinatorial math when we figure out relations and power set. It's a warm-up. So now if you think about over here, we got 2 possibilities for x, right? 1 or 2. Also, for y, we also got 2 possibilities, 1 or 2. Right? So now if you combine them, right, it'll be 2 times 2. So the cardinality is simply equal to 4. Right? What would that be? Well, just for completeness. So this set over here, I'll just say equal to, as if we got some pair. We got 1, 3, 1, 4. I'll explain a little bit more about the notation. It's worth noting. And also 2, 3, and also 2, 4. Right? What I'm saying is this particular set comprehension here, this one here, all the way to over here, is corresponding to this particular set enumeration. All right? Now, I can now explain to you very concretely about the form. Because I said every member in the set is going to be of this form. That's why you see in the resulting set, I got 1 pair, 2nd pair, 3rd pair, and 4th pair, right? You may have a triple, or you have a 4 tuple as well. And then you can see every first element here is corresponding to the range of x, which is in between 2, 1 and 2. And every second element over here is between 3 and 4, which is exactly y. All right? Question?
Did you include that x and y have to be a natural number, so it's taking a float in between, so the cardinality is 4?
So say it again?
So you know how you made it like x and y natural number?
Yeah.
Is that required so it doesn't become a float?
I see what you mean. So you're quite right. If I only got these 2, let's say without these 2, it would be fine too. It will make sense because when you say x should be in between 1 and 2, y should be between 3 and 4, implicitly you're saying they should be natural number, right? But here I'm just saying, I just want to be more short to say x in general is type, is actually natural number. And further to say, it should be in this particular range. I think on paper, you can feel free to ignore these 2. But I believe sometime in the tool, you may have to specify what's their general type first, and then the specific ranges. All right, any question about set comprehension? That's the main takeaway. All right, set comprehension. We'll see more, I promise, when we get to a power set and relation. That one's going to be reaffirming about things. All right, some very basic facts just before we leave this topic here. Again, very basic. So you can say, for example, empty set. On paper, you can either say this is what you have to type, 2 curly bracket with nothing, right, in rodent. On the paper, seen that, right? Just a reminder. And what about cardinality? Well, if you say cardinality of empty set, 0. All right, that's good. All right, if no question here, if you still want to see more example for set comprehension, you will see that in the later lecture. You will see a lot, actually. Almost every relational operators we're going to see today and Tuesday, they will be defined in terms of set comprehension. You have to know how to read them. Okay, just before that, okay, I think I covered everything, but you can just see more example here for set comprehension. I'll leave them to you, okay? And set membership, right? It's a member and it's not a member. That one is also easy. So relations on set. How do we compare 2 sets? And let's now have some bullet point and then we'll show. Okay. Let's say you have 2 sets, S1, S2. We talk about subset. We talk about they are equal. And also we talk about proper subset. Okay. I'm pretty sure you have seen these in 1090. I'm not going to bother you too much about the basic definition. You can read them. I just want to draw your attention to something about subset and proper subset conceptually, and that'll be it. But make sure you read through the basic definition over here and make sure you're convinced, right? We don't need to go over them. That's something you have seen before. I just want to talk about subset and proper subset. So subset first. And if I say S1 is a subset of S2, all right? And then, so here, I'm saying that conceptually I can draw S2 and also S1. However, I'm not necessarily indicating S1 should be strictly smaller. It may be just the same as S2, all right? So here, I just want to say this part over here, which will correspond to S2 set difference S1. Set difference is also defined a little bit later in the slides. So when I say this, S2 set difference S1, I'm saying everything that's in S2 but not in S1. So that's really this part here. Let me be more precise about this. So let me just let it touching. So it'll be easier for me to color. So think about it's exactly over here, right? That's the set difference. Sorry, I'll try to draw faster. All right, that's a set difference, right? This one here is not necessarily empty, but it could be empty. When it is empty, that means they are the same. Okay, so this one here may be empty. So when we say S2, set difference S1 is equal to empty, that really suggests, oh, actually, let me just say that. That's not necessarily true. I think that would be good enough, sorry. Okay, may not be empty. May be empty, may not be empty. And let's now compare with a proper subset, okay? So we can see it side by side. What about proper subset? So for proper subset, we're going to have S1 proper subset S2. So now in this case, we are indicating S1 is strictly smaller than S2. Okay, now how do we visualize it? The same, we're going to have S2 over here, S2, and also S1. And we are saying that this part over here, S2, whatever that's in S2 but not in S1, the cardinality is larger than 0. Right? It's more than empty set. There should be at least one element that's there. All right. Are we good about this? Okay. Alrighty. Let me see the next one. Okay, maybe some exercises. Let me just make sure I don't miss anything. Okay. Okay, let's do some easy checks. Now, can you come up with something for the question mark? What is always a subset of S? Always. Empty set, I agree. Empty set is a subset of every set. I agree. Anything else? S itself. Good. Okay, good. You both said correct answer. Okay. How about this one here? Proper subset. If I replace a question mark by something, it will always fail. S? Yeah, itself, for sure. Can I put empty set and say empty set proper subset S? Would it be always false? Not necessarily, right? That's something. Okay, first of all. Now, if I say something proper subset S, right? If I say itself, always false. And if I say empty set over here, when would it be false? Or when would it be true?
False if S is also empty.
Yeah, exactly. It will be true if it is not empty, right? Good. You guys are getting there. Yeah, just clarify the basic concept. It will be true if cardinality of S is larger than 0. It will be false if, I can write it another way, is equal to empty. Because empty set, proper subset empty, always fail. Okay, next one. So now here, I think that's exactly what I just said, right? So this will be empty, right? So it can be true or false, depending on what S is. Can be empty, can be not empty. So now, is this true? When I say S1 equals S2, that implies S1 is a subset of S2. That's true, right? In fact, whenever I say S1 equals S2, it will imply two things. Let me write it down. If I say a set S1 equals S2, I'm basically saying, if and only if, S1 is a subset of S2, and S2 is a subset of S1. Both. All right? Somehow, this one over here makes sure the cardinality of that is less than or equal to that. And this one here also makes sure the cardinality of that is less than or equal to that. So these two together tells you they have equal size. Of course, they are extra constrained in the definition of the subset, which is going to make sure the contents are the same as well. Right? Well, still basic. Yes. How about this one here? If I know that S1 is a subset of S2, does that mean S1 equals S2? Not really, right? Because if you go back to the diagram over there that we drew, let's say in this particular case, if I got S1 over here, it is a subset of S2. That's okay, but now the difference between S2 and S1, they are actually not empty. In that case, they are not really the same. Okay? Yeah, so these are hopefully straightforward for you. Guys, any question about the definition of the various operators? We good? Okay. So we don't have to stay for too long for these basic notions. Just walk through them. So hopefully we can spend more time on the more tricky stuff today. Okay, we'll get there very soon. Okay, and then I should go to here. Okay, just more exercises. which is here. Some very easy rewriting over here. Just do more. So how do we rewrite this one over here to something equivalent? I'll just tell you the answer. You can say not a member of, that's one way to write, or you can say not the case, element is in S. Very easy, just different ways of writing, okay? And this one here, actually I already said the answer in the previous page, right? So whenever you want to assert about equality between numbers or sets, you can use the same pattern. And I'm gonna give you some practical example in just a moment, right? We're gonna see how we can apply this idea in programming or design. Right, I'm gonna write down for you. So for this one here, I can say, if I got X and Y, X equals Y, if and only if X less than or equal to Y and Y less than or equal to X. Oh, sorry. Something like that, okay? And then for this one, we can do something very similar. If I got S1, S2, they're both sets. I would just say S1 is a subset of S2. And S2 is a subset of S1. So I definitely really meant to say this. Yep, you can see the symmetry here, right? Correspondence, yeah. And we're gonna see some example on this very soon. And for this one, this table here, how about we just do some entries here? I'll let you do the exercise. When I post the notes, I'll put a solution in the cells for you to compare. Let's do a few, okay? Let's say we got 3 sets over here, S, T, and U. We want to know, for example, S, a member of itself. Sorry, S, a subset of itself. Let's say this will be the left, this will be the right. Let's do some very trivial ones. So S, a subset of itself, should be true. And we said before also, S, a proper subset of itself, should be false. And you can do the same for T and also U and U, right? You can do the diagonal. Okay, give it a try. And what about we do one more? Let's compare S and T. S and T over here. Right? Let's just do these two. Okay. Now I got S, which is over here. Is it a subset of this? Yeah, even though they got different order, but order doesn't really matter. Right? Good. That's very good. Now, is S a proper subset of T? No, because they have, in order for S to be a proper subset of T, S must be strictly smaller than T, according to definition, right? So false. Right, you get the idea. So let's not waste your time. So you can do the table. I will include a solution for you when I post the notes. Okay, so you definitely can compare. Just convince yourself. Final one. Is the set difference operator commutative? Which means if I got S1, set difference S2, is it equal to S2, set difference S1? Not really, right? Once you draw the diagram, intuitively it cannot be, right? So let me just show you the intuitive sketch. We don't necessarily have to prove it. So let's say this is S1, this is S2. S1, S2. All right? So let's start with S1. Set difference S2. Everything that's in S1 but not in S2, which would be this part over here. Right? And then we got another one here. S2 but not in S1, so which would be this part here. You can easily find some set, which will be S1, S2. I'll let you do it. You can find that the set difference between these two are simply not the same, right? Corresponding to different parts. So it cannot be commutative. But other operator, like a union intersection, they are commutative, right? Doesn't matter the order you put for the union and intersection. Okay. Okay. Any questions about the basics over here? Okay, so let's now do some interesting example here. Okay, I got 3 different ways to do this, so we can also practice what we have learned. Let's link a little bit to Java, right? So you guys took 3311, so you know something about postcondition. Postcondition means if I try to execute a method, let's say all positive, I'll explain to you what that really means. At the end of the method, you want to somehow assert somehow the output, the return value, can be related to the input value in a certain way. And your postcondition should be as complete as possible, meaning that if there's any faulty implementation that's being executed, your postcondition can catch it by failing it. Okay, that's a postcondition. But we're going to see how we can define that. So here we got all positive is going to take a set of integer. And then it's going to return a set of integer. So set and set. One example here. The input could be, let's say, 2, 3, -1, 4, and -2. That can be the input. And when we call all positive on the input, it's going to return another set. It's going to be 2, 3, and 4. Only the positive numbers. And since it's a set, so there's no duplicates. So this is just one example run. Okay. So now our goal is to write a postcondition. And the first one is going to be the easiest. Okay. Let's say we want to write a postcondition for this method here. And the restriction is you have to use a set comprehension. And this set comprehension here is going to relate between the input and output to tell exactly what the method is going to do. And one thing to note, when you implement this method here, it will be something to do with maybe for loop or just a method call. That's okay. But if you want to specify the postcondition, usually it should be more abstract, more mathematical. Something you can see right away what it is supposed to do. All right. So now, what should this postcondition be using set comprehension? So your answer should be a Boolean expression. That will be the postcondition. And the Boolean expression is going to involve somehow the input, the output, and also the set comprehension expression. For all input? No, actually we don't need for all just yet. If you just want the set comprehension, you can say whatever, set comprehension of what, right? Any idea? I can start you with, how about that? Let's work on this together. I can say, if I try to call the all positive on the input, it's basically going to return to me some value over here. What should that be? The absolute value? Or no, there's no absolute value. There's no absolute value here. Well, of course, you can check to see that's positive, right? But how do we write it as a set comprehension? If I want to write a set comprehension here, right? Now, yes. Okay, so you're talking about x, right? So let me say x. What should be the constraint on x? So you're saying x should be larger than 0? Okay, I'm asking, would you like me to put, okay, thank you. Would that be enough? Guys, let's say this is my postcondition. Do you think this postcondition is right? No. Why not? Integer? Actually, when you say, I can make it a little bit better. When you actually, well, on paper, when you say something is larger than 0, implicitly you say you're comparing number to number. So you're really indicating x is positive already. Okay, let me make it a little bit better. I can say, how about this? Let me say, x is a member of integer, and x is larger than 0. Let's say this is my postcondition. Now the question to you is this postcondition appropriate? And don't forget about the big context over here. We're trying to do this postcondition, and this is actually to be checked at the end of the method for all positive. Is this going to make sure we can capture any implementation fault? That's the question. Is this able to or not? If no, you got to give me a witness where it's not going to give me the right answer. 0? No, it's not possible we have a 0 because x is strictly larger than 0. Can you give me, for example, some input and output sets such that it cannot somehow satisfy this postcondition? Sorry, let me say it again. If you believe if this is inappropriate, okay, I'm just telling you how to judge, is inappropriate. Give a witness pair of input and output such that output is wrong, but it's going to pass the postcondition. But the postcondition passes. So we are trying to somehow judge to see whether this postcondition here is appropriate or not. And if you believe that it is inappropriate, you want to show two things. Number one, the output that you give should be wrong. But the postcondition somehow does not capture the wrong output. It will just tell you it's okay, right? It will give you some false negative somehow. Anyone? Yes?
Postcondition is a Boolean, right?
It's a Boolean. Yes, indeed, this is.
So that any set would work.
Any set will work? What do you mean any sets will work?
So you can pass in a set 1, 2, 3, and then taking into account all possible, that will just give you 1, 2, 3. But the result is a Boolean. It doesn't actually satisfy.
Nothing about the Boolean over here, right? This is to say, whenever you got some output from all positive, I'm just going to compare that against this set over here. Is that a good postcondition, though? So the type is not the issue here. Any idea from you? Not yet? How about this? If I have, for example, let's check this. If the input is like this, and the output is this, number one, we know that this is the correct computation because it does collect 2 from here, 3 from here, and 4 from here, right? 2, 3, and 4. Is this going to pass the postcondition? It is because this one here is the output, right? Oh, sorry. This one is the input over here, and then it's going to give us the correct output. And this output over here is indeed satisfying everything there is positive, right? But now, let me give you this. You can think about it. Here, if I give you input, let's say the same. 2, 3, minus 1, 4, and minus 2. Same input. But now, output, I'll just give to you 4. Let me give you more extreme. 6, 8, and 9. Right? Actually, you know what? This, you see what I mean here? So apparently this is wrong. Agree? But somehow this set here is say, as long as it gives me all positive, that's okay. So somehow this is going to pass. But it's wrong. Okay? So what you should have said is by adding a new constraint. Well, I'll give you the answer. You can think a little bit more. What you should have added is to say, now, not only that x should be positive, but x should be a member of the input. That's what's really missing, guys. Okay? This might be a little bit new to you. Maybe that's not how you were taught 3311. That's okay. But think about this example here. Let me recap. You want to think about it. The lesson I'm trying to bring over here is this. When you think about postcondition, you're basically thinking about how I can formally relate between the input and the output. If I just give you a particular postcondition like this, for example, yeah, if I give you a particular one, how do we judge to see whether the postcondition is wrong? If the postcondition is actually wrong, that means you should be able to come up with some input and output example here, like still satisfy the postcondition. That tells you your postcondition is not strong enough to really capture the error. So here, that's why I have to add another constraint here to fix it. Okay, that's what's happening here. Okay. Now, why don't we do a follow-up exercise on this, right? That's set comprehension, but you just want to also learn about set comprehension expression. Let me just do one more. All right, so now, let's say we want to do the postcondition, right? And this time we want to have the postcondition with the set operators. Right? Again, we want to relate between input and output, right? Let me propose something to you. You tell me if that's good enough. All right, so I'm going to say the following. The all positive input over here, right? You can think about conceptually like this. We're basically comparing this. Let's say this is the input. And this is the output that we compute. Right? When I say output, you can think about output is like this, right? And input, we can divide it into two subsets. There will be some less than or equal to, not non-positive, or there will be some positive. Right? What we really want to extract from the input will be all those positive numbers. So we somehow want to argue that these two sets, this one here and this one over here, are the same set. That's basically what we want to do. Agree? Let me say that again. If you think about the input set, it might contain either positive number or non-positive number, right? If you look at the previous one, positive, also non-positive. We can divide it into two subsets. And then you want to say the output set should really correspond to only those 2, 3, and 4, the subset. Right? So if you want to go back to that example there, so we got 2, 3, 4. This will be the subset 2, 3, and 4. And also we got minus 1, minus 2. Minus 1, minus 2. Okay, and then the output here should be 2, 3, and 4. That's what we want to compare. Okay? So now another way to write a postcondition, Let's try set operators. Let's say subset operator. So what should we do now? I want to somehow argue that this set over here is the same as this set over here. How do I argue that they are the same? One hint for you, right? How do we show that two sets are the same? We just learned about it. You need to show that they are subset of each other. Agree? Okay? So now, if you want to show that they are subset of each other, this set should be a subset of this, and vice versa. Okay? But now, how do we express this set over here? It's basically the subset of the input such that the members are positive. How do we specify this? So what mechanism have we learned so far to specify a subset by specifying a set? If we don't know exactly what's there, but we know its property. Comprehension. Cardinality, well, cardinality is just about the size, right? But now we're more talking about the contents. So we know that every member in that particular subset should be a positive number, right? Okay. So two things over here. Number one, you want to say all the x such that x will be in the input. And x should be larger than 0. Right? Agree? This is how we specify this particular subset over here. Agree? Okay, you just got to practice, how do you use the exact comprehension, right? And then we want to say this is a subset of this, which is the output. And when I say output, I really meant the return value of this. Okay? Is this enough, though? If I want to show that this set here, which is this, is equal to this set over here, which is here, is it enough to just say subset of one way? Not really, right? I got to say it the other way. Good. Okay. This one here, well, I can just put it this. The output is a subset of x in input, and x larger than 0. Okay, I have two exercises for you. You can struggle through them a little bit over the weekend, and we can discuss the answer maybe on Tuesday. Otherwise, it might be a little bit too much about this example today. You want to think about it and see how you can answer the exercise. Exercise number 1. Okay? Let's say three exercises, actually. Exercise number 1. Is the postcondition appropriate? Just by 1. If I say, rather than having both of them being the postcondition, I'm telling you I'm only having this as the postcondition. Is it good enough? If you don't think that's good enough, give me some witness. That's number 1, exercise. Okay? You're going to maybe refer back to where we were over here to think about it, right? And number 2. Exercise number 2. Similar, if I tell you that, is the postcondition appropriate? Just by 2. If I only have this here as the postcondition, but not the first one, is that good enough? If you don't think so, tell me why. Give me a witness, right? So thinking about these two will be very valuable. Okay, I'll let you think about it over the weekend. And the third exercise is, now, I want you to think about, we can actually write these postconditions over here not using set relation. Is it possible just to use predicate logic? Is it possible? Universal predicate logic. Okay? So this will be exercise number 3. Express the postcondition as complete as possible using for all, exist, for example, implication, etc. Just don't use any set operators. Okay, 3 exercises on this example. And we're going to continue from this for this example on Tuesday. Okay, but we can continue with other topics today, right? You just need to think more about this example here. All right. It might be new, that's okay, but you might be asked some question about it maybe later, so it's good to get you prepared, for the mindset. We are really using the logical or set operator we learned in the lecture. We try to apply them into the programming context to see how we can specify complete postcondition, which is important. Okay, let me see what else. All right, we talk about union. Okay, set difference here. You can see that. Okay, how about this? Now it will be the power set. I would really like to go through the definition with you. Why don't we take a 2 minutes break? So after the break, we still got 20 minutes to go over. 2 minutes. Don't go too far. All right, so the next one is going to be more related to how we define towards what a relation is. And once we define what a relation is, we can talk about the various relational operators. That's the goal. Let's see, at least we want to finish the power set. So you can try to digest the definition over the weekend, and then when we come back on Tuesday, we can move on to the relations. Let's see how much we can do. Let's do power set. So what's really a power set? Well, power set, if you say a power set of some set S, is a set. Every member in the power set is a subset. Oh, what does that really mean, right? That's a definition, but I'm going to show to you, and then we'll do one example. Okay? So this is the formal definition for a power set. Let's say this. If you have, this is a symbol. And you can go to that PDF document that I told you in the beginning of the class, right? You can go there to see what a power set looks like in ASCII syntax, right? You might also need that later. Power set of some set S. And guess what? The best way, the only way to define power set is by using set comprehension, right? We're going to see lots of set comprehensions from now on. Now, we're going to have a set comprehension expression here. We're going to say the following. Every member should be of what form? What kind of structure should every member in the power set should look like? We're going to put it on the left-hand side. So every member there, we can say maybe just X, for example. What's really X? We are not really being explicit just yet. And X over here is just a subset of S. Now, I want you to look at here. To define the power set of S, we just want to get all the subset of S and collect them together into another set. Okay? So what you really want to say is each member in the power set of S is a subset of S. Can we just have some very quick check? What will be number 1? What's the member in the power set of S that has the minimum cardinality? Yeah? Empty set, right? Well, when I say minimum, right, almost likely it's an empty set, right? But that's right. So empty set is a member of the power set of S. Now, notice what I'm doing here, right? We're doing something that maybe could be a little bit tricky, but you really want to pay attention to detail. Empty set is a set. I'm saying that a set is a member of the power set of S, because every member in this particular power set is a set. On the other hand, it would be incorrect if I say that. If I say this, Oh, sorry, never mind. This one is fine. Okay, I don't want to confuse you further. That will be good. What about number 2? Number 2, what is the member in the power set of S that has the maximum cardinality? S? Yeah, I agree. S itself. Yep. And now what you gotta imagine is, if I want you to figure out or to enumerate the entire power set of certain set S, which we're gonna do here. We're gonna do it in a moment. You should always understand you will go from the subset that's minimum all the way to the subset that's a maximum, right? And let's do that, all right? Let's follow this definition here. Now, how do we calculate the power set of this? Okay, let's now try that very slowly because this will be very important later on when we need to calculate the relation. Okay, so let's do this very carefully. The power set of, now, 1, 2, 3. By definition, is going to be all the set X such that X is a subset of 1, 2, and 3. Agree? By definition. And I'm going to enumerate them out. We know the smallest one is always the empty set. And the largest one is always the set itself, which would be 1, 2, and 3. And there should be somewhere, there should be some other sets in the middle. So let's think about what might be the most systematic way to enumerate members in a power set. Why don't we try this? This smallest one has the cardinality 0. And this one here has the cardinality 3. To be systematic, we should figure out all the subsets of S that is of cardinality 1 and cardinality 2. Right? Intuitive. So we want to figure out the subset of cardinality 1 and the subset of cardinality 2. That's what we're going to do. But the issue is there may not be just a single one. There might be multiple such subsets. So now, mathematically, we should first know how many subsets are there of this particular cardinality. Right? Can you guys tell me, for this simple example over here, how many subsets are there for cardinality cardinality 1? 3. That's easy, right? 1, 2, and 3. But we're going to generalize it. In this way, it will be 1, and also 2, and also 3. And I'm going to write something down that might remind you what you learned, possibly in Math 2030 about probability, maybe, okay? So the number of subsets. So the number of subsets of cardinality 1 is equal to the choose operator. Have you seen that in math, I guess? Okay. Because I know this set over here is of size 3. Now I want to choose a member from there and make it a set. How many ways are there? 3 choose 1. 3, right? That one's simple calculation. But I'll get to this formula a little bit just to remind you, right? You might need to know this formula for calculation. But I'll get to this a little bit later. Right? What about how many subsets are there for cardinality 2? 3, right? Simple. But we'll get to the more complicated for exercise later. Thank you. So let's now say here. So it could be 1, 2, could be 2, 3, or it could be 1, 3. Right? So each one of them is a set as a member. Yeah, just make sure you separate each member by comma. And the number of subset over here, the number of subsets of cardinality 2 will be 3 choose 2, which also 3. Okay? Okay. Are we okay, at least for this example over here, about how many, about this enumeration of the subset? We're okay with this, right? Okay. Let me talk slightly more about this formula over here. Okay. This might be what you need for later. Also nice to review that over the weekend or before Tuesday. In general, if you want to say n, choose I. Okay, just to remind you how to calculate it, it would be equal to n factorial divided by n minus I factorial I factorial. Okay? So for example, if I have, let's say, 10 choose 2, it would be 10 factorial divided by 10 minus 2 factorial, and then 2 factorial. Let's simplify that a little bit. Is it possible to somehow use this one to simplify this slightly? What would be the result for 10 factorial divided by 8 factorial? 10 times 9, right? Hopefully that rings a little bit bell, from 2030, I hope. That will be 10 times 9 divided by 2 factorial. And now, want to just draw your attention. So here, I have 2 here. This simply corresponds to how many turns you should really have counting from this number here. So this will be 2 turns. Counting from 10. Right, the formula. It's a reminder. Okay. And then, let me see. Okay. Yeah, I would say this formula is important, when we want to figure out sometimes how many relations there could be, for you to derive, you also need this formula. So I would say, please make sure you know that before the test. Yeah, question. Sure, of course. In our particular context, okay, you can think about the n over here. We are doing this particularly, let's say, in the context of, let's say, this. That's the context we're talking about. It's a good question, actually. I should have elaborated that. Let's say in the context of calculating power set, you can think about the n over here can be the cardinality of S, which will be what's the maximum number of element we can get. We want to choose from there, okay? And the I here is really talking about the cardinality of the subset. For example, given, let's say, 1, 2, 3, 4. Now, if I say choose operator over here, I can say the cardinality of 1, 2, 3, and 4. And then I would say, forgot the vertical bar here. And then I would say choose 2. So what does this tell me? It tells me how many subsets are there in the power set. That's of cardinality 2. This tells me the number of subsets of this particular set of cardinality 2. Right? That's what we have. We've got about 6 minutes. I think I can just do one more mention about this formula here. I think that would be good. Okay, how about just one more? But do you guys have any question about this? I would suggest maybe try to review this formula more, right? And then I will give you a little bit more interpretation about this formula, maybe on Tuesday, right? You still want to get used to the calculation of this, right? For example, what would be 100 choose 2? Easy, right? Why don't you calculate, right? Not now. Maybe it's an exercise. And I can give you the answer on Tuesday, okay? Okay, how about one more page? And then I'll let you go. All right. So let's now just talk about just power set, how to figure out how many subsets are there. So there are 2 ways for us to consider. If I want to figure out, so now what do we want to know? Let's say we want to know the cardinality of a power set. Let's say that's what we want to know. All right? There are 2 ways to consider this, 2 possible ways. They are equivalent. But we don't prove it in this course, but you just can know. You just have to know they are equivalent. Approach number 1 is what we just discussed. You can just systematically consider the different subset members in the power set of different cardinality, from cardinality 0 all the way to cardinality corresponding to S. Okay? So approach number 1 is this. We can calculate the cardinality of S by considering this. We simply choose 0 member from there. The cardinality of the subset is simply 0. And this is, by the way, just 1. When you calculate the formula, choose 0 for any n will just be 1, by the way, right? And also n choose n will also be 1. These are just the property for the formula, all right? And this one here really corresponds to the empty set. That's the only possibility you have, okay? And also the other end, we have the number of elements we can choose from, and now we want to choose everything, right? That one corresponds to the S itself, agree? Now what about in between? Right? Let's just do a few more. So now plus, here choose 1. So that will be all the subsets of cardinality 1, right? And also all the subsets of cardinality 2. Go all the way to, could be all the subsets of cardinality minus 1, right? That's a general formula. That's exactly how we figure out the cardinality. So let me just swap the page quickly. That's how we figure out the cardinality of this particular power set over here. We can say 1 here, also 1 over here, and also 2 here, and also, 3 here, and 3 here, right? So you can see the 2 choose operator in the middle. This is one way to interpret the cardinality, and one more. The second one may be something you have seen before, is to consider this. And the second way of considering the cardinality of a power set, it goes like this. Let's say, for example, if I have this set over here, S would just be A, B, and C. So you guys learn about binary numbers, right? If I tell you I have a binary number of 3 digits, how many numbers are there? Okay, it will be, okay, think about this. We're going to enumerate, right? The way to enumerate goes like this. We can say 0, 0, 0, and then 0, 0, 1, and then 0, 1, 0, all the way to 1, 1, 1. Right? You can think about whenever we got 0, that really means exclude the member from S. Whenever we got 1, that means to include the member in S. So now, the first row over here, where we got 0, 0, 0, that means to exclude all of them, which will correspond to empty set, right? So the first one here really just correspond to empty set. What about the second one? What does it correspond to? 1 is but I only include the C. And then, etc. What about the final one over here? That means to include all of them, which will correspond to A, B, and C. Right? That's another way to enumerate all the members in the power set. Now, how many are there? This one may be easier to think about. You don't need a choose operator. Okay, 8, I agree. For this particular case, it will be basically 2 to the power of 3, which is in fact 2 to the power of the cardinality of S. But why? Let's understand this, and then we're done. You're basically saying for every member in the S over here, I got two choices. Either to include it or not to include it. And what are all the combinations there? So you can think about this will be, oops. Sorry, that's my alarm. If you can give me 30 more seconds, I'll let you go. So this one here will just be equal to, in this particular case, 2 times 2 times 2. And the 2 over here means either to include the first element A or not. And the 2 over here is to include the second element B or not. And similarly, the 2 over here is to include C or not. Okay, final conclusion, and then that's it. And then I will recap on Tuesday. So this whole thing over here, we don't need to prove it, can be shown to be equal to just 2 to the power of the cardinality of S. All right? So my point is, you can try to think about the cardinality of the power set either by this formula here or by this formula over here. Okay, that's my point. Right? Maybe tricky, but think about it, get used to it, and then we'll continue from there on Tuesday.